to Geology. Today's lesson is Chapter 1, our minerals. And so last time we did the introductory chapter and took a look at the earth sciences as a whole. Today we want to begin with the foundational material of any geology course, and that is starting with the building blocks of the earth's material. And so we do want to begin with our mineral unit. This will be Chapter 1, and these are considered the building blocks of rocks, which will be Chapters 2's information. So let's begin with our minerals. And so what is exactly a mineral? And so in order for a substance to be considered a mineral, it must be naturally occurring. So anything that is man-made, so it might have the identical chemical composition, but if it's man-made, it's considered not a mineral. So it does have to be naturally occurring. And our next terms in there, inorganic, indicates that the substance has never once been living. So organic chemistry is sort of the chemistry or the study of living organisms, and this would be inorganic, so never once living. And they do need to be in the solid form, okay? Not a liquid, not a gas. Okay? They need to have an ordered internal structure, and so we will be looking at their chemical composition, which does give them sort of an internal networking structure between the bonds of the elements, of a definite internal structure going on, and a definite chemical composition that would only vary within certain limits. And so this will give, and we do identify our minerals through physical properties. So depending on their chemical composition, the arrangement of those atoms, we get the physical properties that we can therefore identify our minerals with. Now a rock is loosely considered an aggregate of minerals, and so the minerals are the building blocks of rocks, and so that is why we want to take a look at those first before we go to our rock unit in Chapter 2 for our next lesson. So we will be looking at the minerals, the characteristics of them, the properties of them, and look at two very broad groups of the minerals with this lesson. And I have brought lots of my beautiful mineral collection to share with you today. Okay, so the basic elements, the building blocks of our minerals. So when we think of the elements in nature, we use the periodic table of the elements. So if any of you had chemistry, you're familiar with that. And of course, there's over 100 that are known, 92 naturally occurring of these elements. The atom is the smallest particle of matter that still retains all the characteristics of the atom, of the element. And so we want to look at that atomic structure. We might feel like we're in a little chemistry lecture here. But yeah, the atom is that smallest kind of particle of matter that still retains all the characteristics of an element. So a zinc atom would retain the characteristics of zinc metal, for example. They would have the same number of protons and neutrons in their nucleus. Okay, so let's look at that. The atomic structure, historically, the atomic structure was proposed by the Greeks. So way back to the Greeks, historically, they proposed a model of the atom where you have a central nucleus, they call it, the central part of the atom, and in the nucleus it contains the protons, which are the positively charged regions, particles, and the neutrons, which are neutral. They do not carry a charge. So within the nucleus you have the protons and the neutrons. And the number of protons in the nucleus of your atom defines which element you have. And that number is definitive of which element you're dealing with, the number of protons. Your neutrons can vary, and we'll look at those here in a minute, the variations. The electrons then are outside of the nucleus, kind of buzzing around. These are the negatively charged particles, and they surround the nucleus. And the more modern view of the atom is, yes, you have the nucleus in the center, and then we think of the electrons in kind of concentrical circles of shells, these energy shells, discrete energy levels called shells. And so that these electrons can be bumped up to a higher energy level in one of these outer shells, and then release that energy and fall back down to the ground state. And so the idea of shells around the nucleus kind of helps us envision what activity is going on with our electrons, and they are the negatively charged particles. And so I like a nice analogy to think about an atom is to take, say, a marble, and we'll call that our nucleus, so the protons and the neutrons in it, and set it on a 50-yard line in a football stadium. So that's the nucleus right there, little tiny marble. And then the football stadium would actually be filled then with various shells around it and filled with the electrons. That's a lot of space in between the electrons. So there actually is a lot of space in an atom, except they're very, very small. But really there's a lot of space in there. So that's a good analogy to envision an atom. Okay. All right, we have a couple pictures here depicting that. Here you've got the nucleus and the protons and the neutrons in there, surrounded then by the electron cloud, they would call this. And over there it's just sort of showing the same thing, but here we have some of those shells they were talking about, first energy level, second energy level, depending on what element we're dealing with. And so that's sort of the idea behind what's going on with the structure of the atom in our elements that are going to build and make up our minerals. Okay. So the chemical bonding, we're actually very interested in the chemical bonding. So we have, those 92 naturally occurring elements, and they are going to interact with one another and create chemical bonds, because with those positive and negative charges, those electrons are going to do some communication with one another. So they're either going to be transferred, maybe accepted by the other elements, but in some way they're going to join together because they become a stable compound in that manner. So we do get formation of compounds by combining two or more elements, and the atoms can gain or lose their outermost. So if we think of the electrons in various shells, energy levels, the outermost electrons can be lost or can be gained by communicating with other elements and form what we call ions. So ions do have a charge on them. They might be positive or they might be negative charges. And so they will, in a manner, kind of transfer electrons in here, and so those oppositely charged ions want to attract, opposites do attract one another, and so in that form they can form what we call an ionic bond. And so they're together a neutral kind of a compound and very stable, and so that neutral chemical compound forms in that manner. So what they're talking about here is an ionic bond. So here's ionic bonding, and here's a little piece of our periodic table, part of it here. So you've got a hydrogen atom, lithium, sodium, potassium, and so forth, and over here some fluorine, chlorine, bromine, and so forth. But you'll notice that what they're showing on here, the red dots on here, are the electrons in the outermost shell of the atom of these elements. And so those are the ones that are going to be active in making chemical bonds. Okay, so as far as an ionic bond goes, it is the transfer of these electrons from one atom to another. So let me write that up, an ionic bond. Be sharing electrons, and we'll show you that. And a really good example, and I think it's the example they use in the PowerPoint, is sodium chloride. And so if we look at sodium on our chart here, sodium has one valence electron, so in its outermost shell, one electron. And chlorine here, if you notice, it's in group 7, and it's set up that way in groups to where this group, they each have 7 in their outer shell. Okay, so sodium has 1, chlorine has 7, and they're going to get together because a little chemistry background here, rule, little atoms either want to completely empty their valence electron shell, at that outermost shell of electrons, either want to empty it completely and have 0, or they want to have a complete set of 8, and that's called the octet rule. The only exceptions to the octet rule are hydrogen and helium. They only want 2 in their outer shell, but all the other elements would like to have 8 around them to make a stable compound. So sodium with 1, chlorine with 7, you can see that sodium is going to transfer, back up here, sorry, thinking of the other one, I'm ahead of myself. Transfer that 1 electron to the chlorine, and it will happily take it because it wants to make 8, so it will very happily cooperate with the sodium. So let's take a look at that real quick. All right, so here we have the sodium with its 1 electron, and chlorine with its 7. I'm just drawing these little dots to depict the electron. You can, if I draw it this way, you can really see how, oh yeah, sodium is very happy to lose its electron, and when it does lose that electron, it has lost a negative charge, so it becomes a +1 charge, so an ion, positively charged ion. And then the chlorine over here is happy to gain that electron, very happy to gain it, and it now has 8 electrons around it, and that gives it 1 extra electron than it had before, so that gives it a -1 charge because electrons are negatively charged. So it has a little minus kind of charge to it, and together this transfer of electrons, okay, this is an ionic bond. So a transfer of electrons is one way that we talk about of getting, and this of course is sodium chloride, which the chemical name or the mineral name for that is called halite. That's just ordinary table salt. Sodium chloride. Okay. Yeah, so this is an ionic bond. Now your PowerPoints did not show you a covalent bond. The covalent bonds are the ones that share electrons. So let me put up the covalent bond. Okay. And my example that I want to use is the quartz, which is silicon dioxide, say quartz. And I think I mentioned last time in the introductory chapter that quartz is Arkansas's state mineral. We will put that on there again for you. We have some of the best quartz. And so sharing of electrons. So we have one silicon atom and two oxygen atoms. So silicon on our periodic table has 4 valence electrons in its outermost shell, and oxygen has 6. And we got 2 of those. So silicon's at the center, and there's an oxygen on either side. Remember, silicon has 4 valence, like that's the dot of an I, that's not an electron. But then we also have an oxygen on one side, oxygen on the other side, and our oxygen has 6. Okay, so if we have, you know, maybe one here, and maybe we've got one down here, sort of a thing. And let's try the other one. So one here, here, 2 here, 2 here. But I'm drawing 2, 4, 5, 6, 2, 4, 5, 6 of our electrons around our oxygens. And so this one here, they want to make the octet rule. So we want to have 8 electrons around each atom here. Okay, so they do what they have to do with their bonding to make that happen, and sometimes we have to make a double bond out of it. So if we're able to put that one down there, bring this one down there, bring that one up, bring this one down, we would end up, I'm going to redraw that over here, okay, with basically this double bond looking thing. Where now they worked it out to where they've got 8 around each atom. So we've got 2, 4, 6, 8 around the silicon, 2, 4, 6, 8 around this oxygen, and 2, 4, 6, 8 around that oxygen. So the octet rule is satisfied for each of your atoms, and this is a neutral compound now, and that's known as a covalent bond. These are actually sharing the electrons, forming a bond, keeping those atoms together in a neutral formation. Okay. So that's the silicon dioxide, which is known as quartz, the quartz mineral, Arkansas state mineral. So ionic bonding was talked about in your PowerPoint, but covalent bonding wasn't. So I just added a little bit about the covalent bonding right there. In your PowerPoint, it is showing you the sodium chloride, or sodium chloride, but sodium and chlorine forming an ionic bond. So yes, the 1 valence electron, it is happy to get rid of it because it wants to empty its shell. And chlorine over here, on the other hand, is very happy to gain that because it would give it 8, and it's very happy with 8. And so you've got a nice bonding pairing because each one has something the other one wants, and they're compatible that way. So that is kind of a synopsis of the bonding of these elements that come together in variations of chemical combinations that make up the mineral composition of our minerals that we're going to be looking at. And so I mentioned the halite is the table salt in there. But if you look at the arrangement, the internal structure of those bonding atoms, okay, so the little blue ones are the sodiums and the bigger beads are the chlorine in there, and you just see the arrangement of it. So it's not just, you know, 1 sodium and 1 chloride, it's many of them together creating the cube here of the halite. And so what's going on with the way that internal structure is arranged will give us some physical properties that we'll start looking at But that's sort of the behind the scenes internal structures of our minerals. It's these chemical bonding that's going on. Okay, so sodium chloride or halite does have that ionic type of bonding, and quartz has a covalent type of bonding. Okay. So quartz is made up of the silicon and the oxygen, and we'll have more to say about what we call our silicates, those that have silicon and oxygen in them. Okay, here's where I mentioned where you can have varying numbers of neutrons in your nucleus. So the number of protons identifies what element you're talking about, okay? But the number of neutrons can vary, okay? So together, the protons plus the neutrons equal what we call this mass number right here, the mass number. So that is the sum of the neutrons plus the protons in your atom. Okay, well, that mass number can change and vary naturally. This can happen in nature, but what's happening is the number of neutrons, okay? The neutrons are the ones that are changing and varying. And so variations of elements like that have differing mass numbers are known as an isotope. And these do occur in nature. They behave physically and chemically just the same as any other of their counterparts, okay? But they just vary, and so they call them isotopes. Some of our isotopes are unstable, and so these will emit particles and energy, okay, in that process known as radioactive decay. And we mentioned radioactive decay in the introductory chapter when we talked about Earth's internal source of energy that's going to be driving our plate tectonics that we're going to talk about. This drives, of course, the volcanism, and it drives earthquakes, of course. So that internal energy source was known as radioactive decay, where some of these isotopes will just spontaneously break down, and in the process they are releasing heat and heat energy, and then of course that heat's trying to make its way out from the interior of the Earth, and we get all kinds of interesting things happening with our plate tectonics. So we'll have more to say about that later. But that's what's happening, is some of these elements will spontaneously decay and form that radioactivity. Okay, and so we would like to start looking then at the physical properties of our minerals. And so we'll just start picking our way through the list. There are several. The first we talk about, so this internal structure we were talking about with our chemical composition and the type of bonding that's going on, the arrangement of those molecules will be expressed externally, okay? And so crystal form is a physical property that our minerals will exhibit. Sometimes you can get very good crystal form. Other times you can't, because they're just not afforded the space to grow. So they're confined or restricted. And so competition for space, rapid heat loss and such, so they're not able to really form the beautiful crystals. But it is an expression of the mineral's internal structure, crystal form. And I brought some examples, my little blocks here, and some minerals that go along with it, on just some of the crystal forms that we can get. Certainly not a complete or exhaustive list, but let me switch over real quick and just show you some representatives. Hopefully it'll show up okay under the camera there. But this first one, this is a hexagonal prism. So we're getting, 6 sides on it like this, and tourmaline. So this is a mineral crystal shape that kind of matches the shapes, the little pink shapes that I'm showing. And hopefully these will show up somewhat. But this does have, a 6 sides to it. So a hexagonal prism, we call that crystal form. Another really good one is quartz has a hexagonal crystal form to it. I might know it actually has a point on the ends of it as well. Yeah, so well, quartz isn't showing up too well on the white background. We'll put him up there. Okay, so that's one shape, crystal shape. Another very interesting one is our octahedron, the fluorite. Again, you probably can't see that too well, but it does have the 8 faces to it, the 8 sides to it. It almost looks like a little diamond shape to it. So the fluorite. Oh well, some of those want to show up under there. I also have a variety that's sort of a bluish color for the fluorite as well here. Kind of a diamond shape to that one. We've got the halite we've been talking about. Our ordinary table salt is cubic. So these would break into cube shapes. So the halite, which is just ordinary table salt, very blocky looking cube shape to that one. The next one that's quite interesting is a rhombohedron. So yeah, it looks kind of cube-like, but it's like leaning a little bit, so it has an angle to it. The calcite is a good example of a rhombohedron. And I don't know if calcite's going to show up very well for you. I might have a darker piece of calcite. Here we go. This might show up a little bit better for you. Again, it looks kind of blocky and cubic, but it leans, so it's rhombus-like, kind of a leaning cube, but the calcite in there. So these are just some crystal forms, crystal shapes that we have. It's a physical property. It can be very diagnostic, but again, sometimes we don't get good crystal formation because of the competition of space. It just doesn't have the room to grow. In some cases, I think of our, state mineral, the quartz, they can get huge. The quartz can be like, 4 feet. Huge, beautiful crystals on those. So they can get quite large if they're afforded the space. But they aren't always afforded that space. I'll be switching back and forth there from camera to PowerPoint, but let's just take a look here. Here they have in the PowerPoint a little sample of a garnet crystal. So you're seeing kind of several faces on it, so a crystal form that garnet could form if it's afforded the space to do so. Here, it made our textbook, the Hot Springs, Arkansas quartz crystals. And so if you remember last time I did give everybody an Arkansas map. Remember that map there? And so pop that under there real quick just for good measure. But Hot Springs, Arkansas. Okay, so right here. Located in the Ouachita Mountains. And so the Ouachita Mountains are made of a lot of sandstone, and you can get cracks and fractures in the sandstone. And then the percolation of the silicon dioxide works its way through those cracks and then crystallizes out. And so you can get lots and lots of beautiful quartz crystals from this region here in Arkansas. We have some of the purest quartz in the country. So we have really nice quartz crystals. That was just an example that they had in our PowerPoints. The Hot Springs, Arkansas quartz crystals. We're kind of famous for that. Quite beautiful. Like I said, those can get very, very large. Another physical property is luster. So luster is how the mineral reflects light off of its surface. So the appearance of the mineral in reflected light. Okay. There are 2 basic categories. One very broad categories, metallic and the other non-metallic. So metallic is, well, it will kind of have a very nice shiny reflective surface to it. Got a little galena here, and it will reflect the light off quite nicely in our metallic group. Non-metallic group, they have several descriptive terms for it, vitreous, silky, or earthy, but it's not going to look metallic with like this galena here, where it would be reflecting light off of it. See if I can get that to work for us, but I don't have a lot of light here. Maybe if I turn the light on real quick, we'll see what happens. It'll be too much for us. So as I kind of tilt it under the light, kind of reflecting light off of that. Here's a good one. Really reflecting light off of it, shining. Okay, there we go, there it is. Very metallic luster, they would call that. How light kind of plays off of the surface of it. Galena was a good example of a metallic type of a luster. And something like a quartz, or it would be more of a silky or a vitreous sort of look to those. Now, yeah, so their example was the metallic luster was the galena, like I showed you under the camera there. Okay, so luster is one. Color, so the outward color. I already mentioned the purple and the blue of the fluoride. So color can be a good diagnostic property for identification of your minerals, but it's not 100% reliable, because we can get contamination in our mixture of, as these are trying to crystallize out, get a little contaminant in them. So they are often highly variable in their colors. It makes them quite beautiful. You can even get banding and swirls of things in them, which is interesting because you can really get some exotic colors in them, and it makes them really interesting gemstones, very valuable because of that. But can't always be really reliable because of all the variations. Yeah, and so we do have just a lot of colorations, and a wonderful set just to distinguish that is the quartz crystals. So I've got a variety here that we can just take a look at. They're all quartz minerals, but they are exhibiting many different colorations. So let's pop some of those under the screen. Some of them might do better on the white background. Some of them might do better on the black background. So we'll just see. I always like to put a little ruler in there so you can have an idea of the size of these. Okay, so I'm talking about kind of making gemstones out of some of these. First one here that I have is what we call the amethyst quartz. So amethyst has sort of a purple. Again, I don't know how well these colors are going to show up for you, but there's a nice little gemstone that we can make out of our amethyst. So they're quartz, but somewhat of a purple variety because it has a little bit of iron contamination in it, giving it that beautiful purple color. Citrine, again, iron is working on the citrine, but it gives it more of a slight yellow to yellow-brown sometimes. Actually, many kind of shades with this one. This is the citrine. There's a little gem that goes along with the citrine to create these beautiful little gems out of them. Again, that's iron. We can get, well, of course, the pure quartz, the uncontaminated quartz. There's some, we call that the glassy quartz. And sometimes they will call them hot springs diamonds. They are not diamonds, they are quartz, silicon dioxide. Diamonds are pure carbon. So anytime you have like a little adjective in front of the word diamond, probably not a real diamond, but they call them hot spring diamonds because they end up putting them in the shape of a diamond, but it's quartz. Okay, but that would be a glassy quartz. We have some smoky quartz. This is a beautiful specimen right here. And this is more of being exposed to the sun. So irradiation of the mineral tends to discolor it. It's actually quite beautiful, but we call that a smoky quartz. So here we go. Smoky quartz, that beautiful one right there, the big one. And then I've got a couple different shapes here of the, get at least one of them completely in view. There we go. The gems that they make out of these. But all of these are silicon dioxide, okay, so quartz, but because of some little contaminant that got in there while it was crystallizing out, it did give variations in the color of the mineral. So color alone might not be the best for diagnostic properties, but can certainly result in some exotic and beautiful gemstones that we can create from these too. So these impurities though are natural, and if something doesn't have impurities in it, if your mineral is just like too perfect, sometimes you wonder if maybe it's been man-made or synthesized. So sometimes we do look for those small little imperfections to let us know it is a naturally occurring mineral. So those were some to deal with colors. Oh, and this one here, you can actually get a lot of banding. This is nice because it's sort of showing you, anybody kind of find those geodes? Those are always fun to find and crack open, and they have like a hollow center where the crystals are forming in, but they have layer after layer here, and again, they can get quite beautiful banding and coloration, all different contaminants happening during that crystallization process. But right there in the center, we see the crystals forming. So these are geodes, they call those. Yeah, so colors. Oh, here's one. It may not show up too well on the screen, but this one has a little bit of a pink. Maybe you can see that pink coloration. So a little bit of manganese got in the mineral mix there and created sort of a pink hue. So the rose quartz, quite beautiful as well. Okay, so those are all some colors, outward kind of appearance of our minerals. Not the most reliable physical property though, just because I mentioned the variable variations that you can get from this. So, but color is certainly something that we can look at with our minerals. Okay. Oh, and then they're showing you in the PowerPoint there all of those that I pretty much showed you. So the amethyst, the glassy, the citrine, and the smoky quartz. We also have one called milky quartz. I don't know if I have that handy. Not seeing it. Oh yeah, well, no. Milky quartz has a little bit of water in it, and we sometimes call those opals as well, but it's a silicon dioxide that has a little water contamination that's gotten into it. So you get that little variation going on with color. It can be quite beautiful. Okay. Well, so if outward color isn't 100% reliable, what is? And so what we talk about is the streak color. And that's the powdered up version of our mineral. And so I've mentioned the pyrite before. If you recall from the introductory chapter, the pyrite is fool's gold. It looks kind of goldish nugget here. But pyrite, switch under here. See that kind of goldish sheen to it. So it fools a lot of people into thinking that it's gold. But gold is actually pyrite is actually an iron sulfide mineral. So the powdered up part of the mineral for pyrite is what we call the streak. And so I've got a little unglazed porcelain tile here that if you scratch your mineral on it and it powders up, you'll get to see what that internal color is. And so if I just set that out here and scratch, several scratches on there already, but that right there, that's black color. So the color, the powdered version of this mineral is a black or kind of a grayish color, leaving a streak, so they call that a streak. That is very diagnostic. You could take that little unglazed porcelain tile out with you out in the mining field and say you get a gold nugget, is this gold or is this pyrite? But if you scratch that on there, gold would actually give you a yellow streak color, and pyrite gives you this black one. So if you remember pyrite, we did talk about it, just to remind you in the introductory chapter, that when they mine for coal and then you burn the coal, well, as they mine that coal, the pyrite is kind of this nuisance mineral that is ever present and comes up when they dig the coal. And so when we burn our coal, we're burning the pyrite as well, and the pyrite does have sulfur in it and releases that sulfur, if you remember this. And the sulfur reacts with water in the atmosphere and will come down as sulfuric acid, so the acid rain problem. A lot of times we try to attribute that to coal, but it's really this pyrite that's in there. So remember what we talked about there. This is a much more reliable little test there, the powdered up form of your mineral. So leaving a streak color for us. Hardness. So a mineral's resistance to abrasion is the hardness, okay? And so we have a scale that we use to judge hardness. It can be very diagnostic, but Frederick Mohs was a mineralogist who came up with a scale, and he took about 3,000 minerals, did his little experiments on it, collecting some data. But he would start scratching the minerals one against another, and he would make his little groups of hardness. So these were very, very soft, and these were very, very hard. And he came up with a scale from 1 to 10, 1 being the softest and 10 being the hardest. So that's his scale of hardness, Mohs scale of hardness. Here they throw in the PowerPoint of the streak on an unglazed porcelain tile there. And they're using a pyrite. It looks like a pyrite or a chalcopyrite sample there as well, just like I did. Okay, so here's the scale. I don't know how well you can see it from there, but you do have these PowerPoints. You do have this in your book as well as reference. So one down here on the lowest or the softest end on the scale, we have talc. So talc's a 1 on our scale. Graphite also. Graphite is what we make pencil lead out of. Graphite is not lead at all in its chemical composition. It is pure carbon, okay? So we just call it pencil lead. I don't know where that came from. But how that's smooth, right? It feels smooth to our skin because our skin is about a 1.5 on this scale. So the talc in the talcum powder feels very smooth to our skin. Gypsum would be another one, and notice here they have 2.5 for your fingernail. So your fingernail can be a very good diagnostic tool. With gypsum, your fingernail could scratch it, but with the calcite, which is a number 3 on our scale, your fingernail couldn't scratch the calcite. So gypsum and calcite are very similar in their look. Let me see if I can find my, here we go. Just look how similar these are, okay? This is the gypsum, this is the calcite. I don't know, about you, but those look very, very similar. So the gypsum we can scratch with a nail, calcite you can't. So your fingernail can be a very good diagnostic tool to help us out with identification of our minerals. Okay, fluorite, I mentioned that beautiful little fluorite. It comes in many decorative colors, the blues, the purples. In lab, for those of you in lab, we have a green, kind of a minty green fluorite. These do make beautiful gems. They're a little on the softer side, but they do make beautiful gems as well, the fluorite in there. So apatite is another one. Apatite's about a 5 on our scale. Notice here glass. So we also use glass as a diagnostic tool. Glass is about a 5.5, and so for those of you in lab, we use the glass to determine, does our mineral scratch the glass or does it not? And then we set up, okay, the hardness is greater than 5 if it scratches the glass, less than 5 if it doesn't scratch the glass. And so we can kind of set up a hardness in that, just a very broad category in that manner. So glass is about a 5.5. The orthoclase feldspar would scratch the glass because it's at a 6 for hardness. So again, having that piece of glass, whether or not it scratches it, can help you sort out some of these identification of these minerals. Our quartz, okay, would be a 7. And so all the quartz samples I was showing you, pretty hard substance with a 7. Topaz, some of our gemstones, beautiful blue topaz, an 8. Corundum, so corundum are sapphires and rubies. Think of that, a 9. Make wonderful gemstones. And then you look at the top there, the diamond. So our Frederick Mohs, he went through and he was scratching all of these minerals, and he ended up with just one mineral that could scratch all the other minerals, but none of those could scratch the diamond. So the diamond is the hardest mineral in nature, okay? So we end up with just that scale there, with the diamond being the hardest natural substance, mineral. Okay, so that has a little bit of something about hardness. That's that resistance of a mineral to abrasion. That is known as its hardness. Okay. Another physical property that we talk about is, how do our minerals break? I'm not going to break any of my minerals, not on purpose anyway, but we have something we call cleavage. So breaking off into or along weak bonds. Okay, so we kind of talked about some of the bonding going on in our different chemical bonds there, but the arrangement of the bonding and that internal crystal lattice structure in our minerals, sometimes we do have zones of weakness that the mineral, when it gets thrown around, will just break nicely into a nice geometric arrangement along those weak zones. We term that cleavage. If there is no nice geometry to the breakage, we call that fracturing. So this first category here is the cleaving. So due to that weaknesses in that crystal lattice structure, tendency of them to break along smooth parallel lines is known as cleavage. And of course you will get a resulting geometry of these different shapes. So varying numbers of planes, maybe angles between the plane. It might be at a 90-degree angle, might be at a 60 or at a 45 or 30. So you do get variations in the geometries that they will form. So I've shown you each of these before, and we were looking at crystal kind of forms there as well. But these are how they would break. And so the first one here is some beautiful fluorite. Remember I told you how it does come in a variety of colors, the fluorite does. So sort of that octahedron shape to it. If you were to break it, all the pieces would end up being that same geometry. The one in the center is the halite, the cubic shape. So if you think of your table salts, those are very, very tiny cubes, okay? You might need to really look at your salt someday from your salt shaker But those are very, very small little cubes of the salt, so that all the geometry would be the same when we break the halite, the sodium chloride or table salt. So halite breaks cubic, and then remember the calcite. It kind of is a cube, but it leans, so it's the rhombohedron shape to it. So they would all cleave like that. So this is the calcite, showing and exhibiting that perfect cleaving. So along those weak zones, we're getting these shapes, these geometries. That's cleavage. Okay. Now, fracturing, on the other hand, it's just a random break. They're not going along any particular geometry. And so sometimes you can get sort of this conchoidal type of fracturing. It almost looks circular-like. Quartz actually breaks like that. Quartz will fracture, and kind of like glass does, that conchoidal fracturing. I think there is a picture. But fracturing is the absence of cleavage when a mineral is broken. Okay, so again, I'm not going to break my minerals, but there's a nice picture. This is the conchoidal fracturing. So seeing how it's just sort of a random break. There's no set geometry to it. And conchoidal in that it is sort of this semicircular pattern to it in there, but just random geometries when these break. We call that fracturing. Okay. Nope, went the wrong way. Hang on. Let's go back to the specific gravity in here. This is the weight of a mineral compared to the weight of an equal volume of water. So we use water as our reference, and water is a 1.0 specific gravity, and so you compare your minerals to that, what 1.0 would be for water. Yeah, on average, our minerals are between 2.5 and 3. That's pretty common, but we do have some. I've mentioned them before. Well, galena is very, very heavy for its size, so it has a high specific gravity. It's about a 7.5 in comparison to an equal volume of water is how you compare that. But galena has that heft to it. It's very heavy. I also mentioned in the introductory chapter the barite. My barite. Remember the barite, the significance of the barite. So barite is a barium sulfate mineral, has a decent heft to it. It's about a 4.5 specific gravity. And if you recall, when I was talking about how we were extracting the oil using the hydraulic fracturing or the fracking method, where we used a drill mud of barite. The barite was a little bit heavier. Drill mud, with all that water they were putting down through there, were the sandstone and the shale, which ranged, 2.5 to 3. They were lighter. Those would float up on the top of that drill mud, and you could sieve your sandstone and your shale out to keep that hole open, the pipe open. That was the significance of the barite. So it does have a bit of a heft to it, so a higher specific gravity. So some of them, this can be diagnostic for some of our minerals. Okay, that was the barite, so try to remember that one. But specific gravity is a physical property of our minerals. There was that conchoidal fracture. Some other properties. So these are some special properties. Not all of our minerals exhibit these properties, but a few of them do, and they can be very diagnostic. So magnetism is one. I'll probably just go to the camera on this, and then keep in mind this list. We'll work our way down the list there. Though I do want to show you some of these. So magnetism. Magnetite here, okay, magnetite is an iron oxide containing iron atoms and oxygen atoms, and it will attract a magnet. So I have a little piece of magnet here, and it will attract that magnet. That won't fall off. Okay, so it's attracting a magnet, so it exhibits magnetism. That's a special property of magnetite. So a very aptly named mineral. Okay, the reaction to hydrochloric acid is another physical property that some of our minerals have. our carbonate-containing minerals will react with hydrochloric acid. So that carbonate content, CO3, which is a carbonate content, will react with the acid and actually neutralize our acid by the products that it makes. It releases carbon dioxide in it, and so they'll fizz and they'll bubble or effervescence when you have that carbonate content in it. So the calcite, which is a calcium carbonate, of course has the carbonate in it, and it will react quite vigorously with the acid. The limestone, which is what I have here, limestone we will learn when we get to our rocks, the chemical sedimentary rock. Limestone has calcite in it, okay? And so let me just put some little bit of the acid on it, and it will fizz and effervesce, so react to acid. So let's go ahead and put some, and it's very vigorously, you can see the bubbles being generated there, hopefully on that screen. So right away, if you're out in the field and you have your little bottle of hydrochloric acid with you, you can put a drop on there. If it reacts vigorously, then you know it contains a carbonate mineral, probably going to be your calcite, so you can tell if that was a limestone rock or not. Something else that does also react is dolomite. Dolomite is similar to a calcite in its mineralogy, meaning its chemical composition. When I say mineralogy, it's the composition. Dolomite is a magnesium calcium carbonate, but it does have the carbonate in it, and it will react, but not quite as vigorously as your calcite will. So reaction with the hydrochloric acid is definitely a very diagnostic property. Double refraction. See if I can get this to double refract. I'm going to need some typed print. I think I might have a little bit on the back side here. Move these out of the way. Double refraction, our calcite. Okay. Oh, this is good. How can you be able to prepare for the next exam? Well, read the book, buy the book. Anyway, let's try to put this piece of calcite over that typed print. Okay. And I don't know all that showing up. There we go. But you do see a double image. There's a B, there's a B, right? B and a B. What is happening within that crystal lattice, internal structure of our calcite, is that it is splitting the light. So as the light comes through, it splits it or bends it, so refracts it, and causes that little double image. We call that double refraction. So it has to do with the internal structure of that mineral, and calcite does exhibit the double refraction. Taste was another one on our list. Of course, the halite, right here, the halite, the sodium chloride, you lick that, and it's going to taste salty because it is. It's ordinary table salt. So taste is very, very diagnostic. Oh, and sometimes we like to purchase maybe this fancy pink Himalayan salt. It's kind of expensive, the pink Himalayan salt. Oh, it's rather beautiful and decorative if you're going for that, but it is like 98% sodium chloride. So it's just ordinary table salt. It might have a little contamination, given that little bit of coloration, right? The variation of coloration, but it's honestly not worth the price. They really price gouge you on the Himalayan salts. It tastes just like regular salt. So unless you're going for the pretty presentation kind of thing, I would steer clear of that. Okay, so taste, very diagnostic. Smell is another one. I don't have a sample of it with me, but the kaolinite, a clay type of a mineral. If you get that wet, you moisten that, and then smell it. It smells very earthy-like. We have another one that you all in lab will work with, but I've got a sample of it here, and it's called the sphalerite. The sphalerite is a zinc sulfide. The streak of it, so if I scratch that against the streak plate and smell it, it has a rotten egg, very sulfur type of a smell to it. So that's very diagnostic. You might have your little streak plate with you out in the field, scratch that against it, smell it, very diagnostic because of that sulfur content. Okay, all right, so smell. Let's go back to that list and see if there's anything that I'm missing. I think they had malleability. Yeah, malleability in there, and that is how you can shape or form. Maybe if you were going to hammer out your mineral, does it shape and bend and form? Malleable. Okay, so malleability is one. Elasticity is another one. This is how well is the mineral going to be able to be stretched and then return to its normal shape. Okay, so elasticity. How elastic is it? So these were some special properties of our minerals. Not all of them exhibit these, but they can be very, very diagnostic for us. So, physical properties. So as I mentioned, there are thousands of minerals. Onwards of about 4,000 minerals have been confirmed and identified. Some they have to do chemical X-ray analysis to determine the exact chemical composition on these, and they do every now and then come up with a new one that gets verified again by the X-ray analysis of exactly what chemical composition are we dealing with, and if it happened to be a new combination that's been verified, then we got a new mineral kind of thing. So around 4,000 minerals, but those that are going to be important for our rock forming minerals, you know, common in the rocks that make up the Earth's crust, there's a lot fewer. So only about a dozen members to remember in there. Yeah, so common ones that make up most of the Earth's crust. Composed of, so remember the periodic table where we had like 92 naturally occurring elements? Well, thankfully, only about 8 of those elements are important in rock formation, so not a whole lot. They make up about 98% of continental crust that we deal with. So here's a little pie wedge in here showing you the elemental abundance of the various elements that go into making our rocks. Okay, so here we've got oxygen is the biggest wedge, so within the elemental crust, oxygen is the major component. Also, very large wedge is the silicon, right? So the silicon and the oxygen is a very large portion of our elements involved in rock formation of the continental crust. Then notice how we've got little wedges of various other metals. So we've got iron, magnesium, potassium, sodium, calcium, aluminum, and then a little wedge here of all other elements, some other elements mixed in. But the majority, as you see, is silicon and oxygen. That is going to make up a very large group of minerals, branch of minerals, known as the silicates. Silicon and oxygen, they call that a silicate containing. That's like our largest group of minerals are silicates because of what the Earth is made of. A lot of silicon, a lot of oxygen, okay, in that. So that little wedge is interesting to keep in mind there. Okay. So here we have that most important mineral group. The silicates is one group. And if it's not a silicate, we call it a non-silicate. So silicates and non-silicates. But let's look at our silicates. It's the most important mineral group. It comprises most of the rock-forming minerals, very abundant due to that large percentage of the silicon and the oxygen in Earth's crust. So here's our basic building blocks, silicon and oxygen. Got a little model here, the fundamental building blocks. So this is the building block, the basic building block of silicon and oxygen. We call that the silicon-oxygen tetrahedron. So if you would imagine, we'd have one silicon at the center, and then 4 oxygens around it. And so it has this tetrahedron shape. In chemistry, this is a tetrahedron shape. And so that's what they call that, tetrahedron. Okay. Fundamental building block, 4 oxygens are surrounding 1 silicon, okay, atom. Oh, and here's just another one. You probably can't see the little red bead in the center representing the silicon, and then the 4 styrofoam balls around there are the oxygen atoms. So that's the tetrahedron shape that they're referring to. And they've got a couple illustrations as well. Silicon in the middle, surrounded by 4 oxygen atoms. The silicon-oxygen tetrahedron. Okay, we call that silicon-oxygen tetrahedron. Okay, so it does, this is sort of the basic building block of our silicate mineral group. They all have silicon and oxygen in them, plus some variation of those other metals. You know, we had iron, we had magnesium, potassium, calcium, sodium, there was aluminum in there. So they do throw in some of these other metals in varying amounts. And so the chemical composition is very important in what our mineral name is, right? So here we have a chart that lists our silicate minerals. And the interesting thing about silicate minerals are that they all crystallize out of magma, so molten earth material, where it's all melted down, okay? These all crystallize out of magma. And they do it in a set order, okay? A set series on how these will precipitate and crystallize out. And it's based on temperature. So as the magma begins to cool, certain minerals are going to come out at high temperatures, and as it continues to cool, a series of minerals will crystallize out according to temperature. And that is how this chart is set up here. And I know you're not going to be able to see the chemical compositions from the PowerPoints very well. You do have a copy of those on Blackboard. And it's not that you need to memorize any of the chemical compositions. It's not about that. It's looking at this general pattern of what's happening to the chemical composition as we go to cooler and cooler temperatures as to which minerals are going to crystallize out. So first off here, we have the olivine group. Olivine, again, it has that silicon and oxygen in it. That's what makes it a silicate. But it has a little bit of magnesium and iron in its chemical composition. Magnesium and iron make the minerals rather dark, okay, darker in color. So olivine is a green hue to the mineral. But what's even more important is what's going on internally with their structure. So independent tetrahedrons with a little bit of magnesium and iron hanging on to that structure, okay, this tetrahedron. Single independent kind of tetrahedron, and that is our olivine, okay, coming out. The next group, as temperatures cool a little bit, still molten but cooling, the next mineral group to come out are the pyroxenes, okay, also known as augite. Okay, what's going on in there? We've got one less little oxygen because what's happening in their internal structure is they're starting to form a single chain here. Those little tetrahedrons are linking up and combining, okay, to a single chain. Okay, we call that the augite or the pyroxene group. I'll show you some samples of these as well. Again, a very dark mineral. It does have the magnesium and the iron content, making it dark. Okay. Next one that will come out, temperatures are cooling again, cooling a little bit more. So whatever we got left now, we're getting the amphibole group. This is also called hornblende. Okay, but look what happened internally with its structure. See, we had a single chain there, but now we're getting a double chain. So the single chains are linking into a double chain. So that's that internal chemical structure going on in there. And notice in here, we still have magnesium and iron in there, but we've started to add a little bit of the calcium metal into the mix, okay? And so a little bit less of the magnesium and iron, still has it in there, so it's still a dark mineral, but a little bit less. Now we're adding a little calcium in there. Again, according to temperature, these crystallize out. So as you continue to cool, you get different mineralogy or different chemical composition. So let me just show you under the screen here. And we'll try to show you some of these actual samples. Here is an olivine. Okay, so that greenish kind of hue to it, and here we have a cute little gem that they made of the olivine. Here's the pyroxene, dark mineral, and here is the amphibole. That kind of order there. Here's some amphibole. Okay, again, very dark, on the dark side of the coloration on these. So those are the first three that come out of our series of silicate minerals. And so if we go to the next PowerPoint, we're continuing to cool, right? So we're cooling our magma, and the next groups to come out are called the micas. These are micas. We have a biotite mica and a muscovite mica. Biotite mica is the darker one, right here. Muscovite mica is the lighter one. But look what's going on with their internal structure. The sheet silicates. So the micas are what we call sheet silicates. Hopefully you're understanding me. But that silicate group that is a sheet silicate are the micas. So the biotite and the muscovite mica. And they will slough off almost like sheets because of their structure. Okay, that internal structure, they'll just kind of like peel off even. So the darker one is the biotite, and the lighter one is the muscovite. I'll show you these a little closer here in a second, once we kind of get through our group there. But the micas, okay, sheet silicates. Okay. Next in line are the, we've got a potassium feldspar. Okay, so potassium feldspar, these are three-dimensional networks. So now you see this is just a three-dimensional network in the arrangement there. Let me back up to muscovite because of the coloration difference. Biotite mica has the magnesium and the iron in it. It also has potassium. Now we're getting a little potassium in there. Muscovite mica does not have the magnesium and the iron in it, and so it's not dark like the biotite is. So our darker minerals are going to have magnesium and iron in them. That's what we call a mafic mineralogy. Magnesium and iron together, we call it mafic. But that will become important to us when we start talking about plate tectonics and the difference between oceanic crust and continental crust. So mafic, you might tuck that little term in the back of your mind. But that's the magnesium and iron content. That's what makes that mineral so dark. But in the mica, the muscovite, it doesn't have it any longer. We got potassium and aluminum in there, but no magnesium and iron. Okay, down here with our feldspars, so the potassium feldspar, as you can imagine, has potassium in it, but it's an aluminum silicate. So it's got potassium, aluminum, and then silicon and oxygen in it. No magnesium and iron. All the magnesium and the iron has now reacted out, crystallized out in our series before. So that's no longer in the magma. And so as the magma continues to cool, it will crystallize out whatever's left over in there. And so we've got potassium and aluminum silicate, okay, for the potassium feldspar. And it actually does come in a variety of colors, but this one's sort of that salmon pinky color to the potassium feldspar. We have over here something called a plagioclase feldspar. These have a variation of calcium and sodium. Aluminum silicate, we call them. Variations in the amount of calcium to sodium. And so a pure kind of calcium plagioclase would be what we call an anorthosite. And a pure sodium plagioclase is an aldite. And in between, you can get many, many names of minerals in between, depending on what percentage of calcium do you have to percentage of sodium. So you can get many different names in between there. But we call those the plagioclase feldspars. And so they do vary in the amount of calcium and sodium, aluminum, silicate. So we can get, and they didn't even show you a picture of those, but I will try to show you an example of one. Okay, so now we got all that calcium, all that potassium and aluminum. Well, the last mineral to crystallize out of a magma is pure silicon dioxide. Pure silicon dioxide. Quartz is the last one to come out. Again, it still has a three-dimensional network, but quartz is our last mineral to crystallize out of a magma. And so this all was according to temperature on the series of how these did crystallize out. But let me pop under real quick some of the other ones that we mentioned. The biotite is the dark one here. A big piece of biotite there. The lighter one here is the muscovite. You can kind of see the sheet nature here. Like I can almost split some of these off of there. Right? Split that off. Okay. Sheet silicate are the micas. Okay, and I got a bunch of those pieces in the bottom there from them sloughing off. Okay, so those were the micas. And then we have the feldspars. So we got the variety of the potassium feldspar. I don't know how well that one's going to show up because it's kind of light. So sort of that pinky color in it. And then I've got some, we call this labradorite. It's a calcium plagioclase feldspar. And it can be quite beautiful. I don't know how well it'll show up on here, but it has a very beautiful kind of a blue iridescence. I don't know if that's, yeah. I don't know how well you're seeing that, but there's these little flecks of blue in it, so it has that little almost like a rainbow sheen to it on the surface of it. They actually do polish these up and make tiles and various gemstones out of them, jewelry out of them. But that is a calcium plagioclase feldspar. Kind of a beautiful specimen there. Well, I actually do have a gemstone that's broken, but I've got a little piece of one that's been polished up, so they make a little cabochon out of it. So, we can stay put. But it does have sort of this sheen coloration to it. It is a blue kind of beautiful color to it. That is a calcium plagioclase feldspar. And then, like our last one to crystallize out, I know I've shown you it several times, would be the quartz mineral. Okay, the quartz. So these are what we call the silicate minerals, the representative group of the silicate minerals. So they all have silicon and oxygen in them, in their chemical composition, and then varying metals. Magnesium and the iron ones tend to be darker in color, and then as you go down the series, we no longer have the magnesium and iron because they crystallized out, and you start to get the potassium and the aluminum and the calcium and the sodium, and then those all react out, and then you get left with just that pure silicon dioxide, the quartz, as the end member of our silicate minerals. Okay, so that's one group, and that's a very large group of minerals because, again, the abundance of the silicon and the oxygen in our Earth's crust. Okay, so that was that series of the silicate minerals, and they're going to show you here the feldspars, and the feldspars are out of our silicate minerals. The feldspars are our largest silicate group. So Earth's crust, the continental crust, has an abundance of the feldspar in it. So it's really number one, like the most abundant mineral in the continental crust. And then I would say quartz would be our second most abundant mineral in the continental crust. So, but the feldspars are really a very large portion of the crust. Okay, and again, quartz is made completely of the silicon and the oxygen, pure silicon and oxygen. So another group that we have are what we call the non-silicate groups. So these do not have the silicon in them. Some of them can have oxygen in them, some of them do, but they don't have the silicon and the oxygen, structure in them. And now these only comprise about 8% of the Earth's crust, so they're not as abundant as our silicate group. But a lot of times we're going to find them as little constituents within our sedimentary rocks, which we'll talk about those when we get to our rock unit. But I do want to go through those. I'll have some nice samples of a lot of these. But again, the chemical formulas, you won't have to memorize any of that, but this is just showing you how they're categorized, okay, with their chemical formulas. And they also give you kind of some of the economic uses for these, what the mineral name is, and so they've got them separated into their mineral group. And so usually in the chemical composition or chemical structure, the group is like the last part of the chemical compound formula. So our first group up there, they refer to as the oxides. So they're going to have oxygen in their chemical structure, the second part of their compound there. So all of these have oxygen in them. And there's one on here that might surprise you. Ice. Right there, ice. H2O. So water, ice, is considered a mineral. So our definition of a mineral has to be naturally occurring. Yes. It has to have a definite chemical formula or structure to it. It sure does, H2O. A crystalline lattice. So when water does freeze, it does give a crystalline structure to it. They do have to be solids, inorganic solids, right? So ice, water ice, does meet all the criteria to be considered a mineral. So we do call ice a mineral. Liquid water and water vapor, gas, no, but the solid form of water is a mineral. So maybe that might surprise you. Some of these other ones, the iron oxides, there's a couple varieties in there. The hematite and magnetite we showed you. The corundum is an aluminum oxide, so it's aluminum and oxygen. The corundum, I think I mentioned before, these are some beautiful gemstones. Those would be the sapphires and the rubies. So I think sapphire, are the bluish tinge coloration variations that we can get. And the rubies are reddish in color. And these are like birthstones, right? You think of all the birthstones that we have. I believe sapphires are the September birthstones, and that ruby reddish corundum is the July birthstone. So if you're a July baby or a September baby, you might know your birthstone. And so that's referring to the corundum, and these are aluminum oxides that are some gemstones that we can get. So let me show you some of those. Try to move some of these as quickly as possible. So many minerals. That I was referring to. Okay, so the mineral itself doesn't look like much until you get that cut and you get it polished up. So the blue coloration are the sapphires, and the red coloration of that variety of corundum is the rubies, right? And rubies, I believe, was the July birthstone. Sapphires the September And we have also, we talked about the hematite. So these iron oxides. And so hematite, don't think we had a chance to see the hematite, but it does have sort of a rusty kind of appearance, that iron kind of oxide look to it. That would be the hematite. And then we did show you the magnetite before. We had showed you that magnetite, right? It was attracting a magnet. Again, an iron oxide, a little different configuration than the hematite formula. But these are all oxides. They end with like an oxygen, and then they have a particular metal at the beginning of them. So these were the oxide group. Again, non-silicates, because they don't have the silicon and the oxygen in these. These are the non-silicates. Our next group are the sulfides. Sulfide group. So those are going to end with sulfur, right? See all the sulfurs in there? We've got sphalerite. I did show you that sphalerite. That was the one. It's a zinc sulfide that you scratch it and it smells like rotten egg. So our sphalerite. And then we've talked about the galena a few times. The one that has like a really heavy heft to it, a metallic luster. We talked about it then. We talked about it with that cubic kind of shape, the specific gravity. So we talked about galena a few times. And if you remember in the introductory chapter, just a quick review, we did talk about how galena here in Arkansas, we did have some source of that in northern Arkansas, to where they named a town after it, and they called the town Lead Hill, because galena is a lead sulfide, right? It has that lead in it. So again, geology really does surround us. It's embedded in our historical of the names of some of our cities. So geology, yeah, it's all around you. Sometimes you just have to open your eyes and look for it. So let me pop those under there. These sulfides, the various sulfides. Okay, so I mentioned the galena, lead sulfide, mentioned that sphalerite. Sphalerite is a zinc sulfide that has that rotten egg odor. And there's one that we have talked about over and over again, the pyrite. Okay, that's an iron sulfide, that nuisance mineral that's dug up with the coal, right? Causes that acid rain problem. Okay, and then I think they had the mercury sulfide in there as well. So I've got a little bit sample. It has a pretty red color to it. It's called cinnabar. Okay, but it's a mercury sulfide. So all of these have sulfide in their chemical composition. So that group is known as the sulfide group. Okay, and then they take a look at the sulfates. And so sulfates are the SO4. Okay, so SO4 in their chemical composition. So that first one there, the gypsum, I think I popped the gypsum under there just for a brief second when I was comparing it to calcite. But calcium sulfate, and then they've got 2H2O. So they call that a calcium sulfate dihydrate, which just means that there are two water molecules loosely bound to the crystalline structure of the calcium sulfate, it's gypsum, anhydrite. We don't have the water molecules attached, so it's just calcium sulfate. It's like we heated it up and burned out the water vapor. Okay, so that's an anhydrite. And then there's good old barite again, a barium sulfate. That barite, remember that drill mud, right? The barite. I know I keep saying that. Must be important if I keep saying it. So that's our sulfate group. Let me show you those. So here we have gypsum. Actually, I've got two variety of gypsum here. They're both gypsum. Don't know how well. Let me turn the light down. See if that makes any difference for you on the screen. These are both varieties of the gypsum. We call this the selenite gypsum. We call that the satin spar gypsum. It's a little more fibrous in its crystals, the satin spar. But we actually do mine some gypsum in the Murfreesboro area. Let's see if Murfreesboro, yeah, it's on our map here. Here's the Arkansas map again. It's in the Gulf Coastal Plains, but it's very near our Washita. That's very crooked. There we go. Here's Murfreesboro, right there. But near the Washita, but it's within the Gulf Coastal Plains. We do mine for this gypsum there. They make sheetrock out of the gypsum. So I've got a little piece of sheetrock here that they will make, you know, you'll put cardboard in between it, but they grind that up, the gypsum, and make sheetrock out of it. It's a big industry there. So mining for the gypsum resource that we have here in Arkansas in the Murfreesboro area. So it is used in the building industry as sheetrock is a common use for our gypsum. And then the barite, if you remember, that sulfate mineral with the high specific gravity, I keep saying it, that's used in the hydraulic fracturing, that oil-filled drilling mud. If you remember that, that's our barite, okay? And you also can get barite to form what they call the barite rose. They're kind of pretty here. The barite rose. There's a little concretion there that kind of looks like a flower. And so they call that the barite rose. But again, a barium sulfate for that, and a calcium sulfate for the gypsums. So those are our sulfate groups. Non-silicates, but that's how they're kind of set up, is by their chemical composition. Now we're at the category of native elements. So these are just a single element that in aggregates of it, we can mine for them and get ores of them. So gold is one, copper, okay, they've got their uses over here. Carbon, so the diamond is pure carbon, as I mentioned. Sulfur, pure sulfur, we'll show you that. Graphite is also pure carbon. The diamond's pure carbon, graphite's pure carbon, so why are they so different? So I want to look at that, what's going on internally with their structure, to why they're so different. Their properties couldn't be more opposite. Graphite's like a 1 on the hardness scale, diamond's 10, diamond's like the hardest mineral. So why the difference? They're both pure carbon, so we do want to look at that. Silver is another one. Platinum, another one. I don't have any platinum, but I do have some of these other ones here that I'd like to share with you. Several things here. The gold. I'm going to do a little comparison here of the gold. Here I've got some native gold. This is from Colorado sample. What it is, it's in a little vial, and the vial has like a black background on it, so you can kind of see the gold in there. I don't know how well some of this is going to show up on the screen there. This one has a combination of gold and silver kind of mixed together. You probably won't be able to see it, but I'll try to maybe magnify it. Not so sure. A little silver in there, a little gold. Don't know how well that's showing up there. But yeah, we've got some little gold flakes in that one up there. So silver, gold, silver, argentum is its Latin name, and North Little Rock, if you're familiar with North Little Rock, actually used to be called argentum, and it stemmed from the silver that was mined, and it's back in its history. And the farmers market area, that market area is still called Argenta, stemming from that historical earth resource of silver in its past history. So again, geology has a lot to do with how we name a lot of our cities. And then the yellow one here is the sulfur. It is naturally, it does have that yellow coloration in it. Here we have some copper. This is an Arizona specimen. Some copper metal there. Okay. So these are just some of the elemental ones. I did mention that diamond and graphite. Okay, let's look at those two. The diamond, I don't know what you're going to see that diamond in there. It's probably not going to, I don't know, there's one right there. There's actually two in that little container. But the pure carbon in both cases, why are they so different? One on the left are graphite. That's our very soft, like a 1 on the hardness scale. It sloughs off, makes good pencil lead. It's not lead, it's carbon. But it makes good pencil writing utensil. And then pure carbon in the diamond form. Very hard, a 10 on the scale. Also, when you look at them, graphite, light will not go through it. You can't see light through it. Diamonds, that's the whole idea of the diamond. That's what gives it the brilliance, that light's going through, playing on that internal structure and giving you that brilliance to the diamond. So what is the difference? Well, what we call these are polymorphs. So they're same chemical composition, but yet very different in their crystal structure. So polymorphs, we can get all that on there. Same composition, different crystal structures. So what's happening with the bonding of that internal structure is what's going on with these. And so with the diamond, we have the strong covalent type of bonding, the sharing of the electrons, hardest mineral, right? So that will affect arrangement of those elements, will affect the physical properties, right? It's a very good example is diamond and graphite. And then the graphite has some weak bonding going on. They call them the van der Waals bonds in there, but they're weak, and to the point that, yeah, the mineral is going to break and kind of slough off very easily there. But strong bonds here, but in between here, almost like chicken wire arrangement in our graphite, creating some weakness to where that's going to slough off right there. These weak bonding, those van der Waals bonds, creating a very soft mineral. Light doesn't penetrate through the graphite. So same chemical composition, pure carbon, but yet because of the way it's arranged and bonding, very different outward physical properties of it. So that's a polymorph, we call that. Rather interesting situation for those two. These are all sort of what we call the native elements. And so we're ready for the halides. The halide group. So halides are a group on your periodic table. It's group 7 on the periodic table, and it includes fluorine, bromine, chlorine, iodine, bromine, these types of things in group 7 in there. So that one of those elements will be in your chemical composition. So here we have the halide that has the chlorine in it from the halide group. Kind of how it gets its name, halide, halite. But it's a sodium chloride, common table salt. The fluorite, we kind of showed you the fluorite with the different crystal forms. That's a calcium fluoride, used as a catalyst sometimes, or steel making, used in steel making. Potassium chloride is called sylvite. Sometimes sylvite is used as an alternate to sodium chloride because if you have to watch your sodium intake, your doctor tells you don't use salt, well, sometimes you can use the potassium chloride and have the sodium in it as an alternate kind of substitute for salt, table salt, and sylvite in there. But the thing about potassium chloride is dosage, because that is the substance they use with the death penalty to stop your heart. So too much of a dose will actually stop your heart, but in the right dosage, it can be good for your heart. So they also do use some fertilizer with that as well. So let's take a quick look at the halides, which we've kind of looked at some of these before. Here's my sodium chloride, chlorine. Okay. Oh, fluorine comes in a nice purple color. So this is the calcium fluoride, the fluoride. We've got some blue there, and the purple. And as I mentioned in lab, for those of you in lab, there is a green color as well, kind of a minty green color of that, the fluoride. And then this is the, won't show up there, but the halite. So the ordinary table salt, cubic table salt. I didn't have my sample of my sylvite potassium chloride. They are very hygroscopic, the halite and the sylvite. They want to absorb moisture from the atmosphere, so it's like very humid today, and my sylvite's kind of a watery puddle right now. So I didn't have that one, but these are what we call the halites, okay, the halites. Lastly here, we have the carbonates, and we did talk about the carbonates, the calcite, and the dolomite, and I showed you how they react with hydrochloric acid, right? But they have that carbonate, that CO3 polyatomic anion in their chemical structure. And dolomite is a mix of calcium and magnesium in it. So a lot of times we'll use those in cements. They're good for that. But these are the carbonates. Let's see, the dolomite I don't think you got to see yet. So dolomite is pinkish color, or dolomite there. I got a really big one here. And it's a combination of, it has some calcite right alongside of the dolomite. The pinkish color is the dolomite. And you'll see that in nature because their mineralogy, their chemical composition is so similar, right? The calcium carbonate and the calcium magnesium carbonate, the dolomite. So you'll find them together in nature. Okay, so this is the dolomite right next to a calcite. And I did show you the variety of calcite, I think. I'm losing my calcite. Yeah, but it will have, this will be like the calcite. Remember that rhombohedron kind of shape to the calcite in it. Calcium carbonate. So the shells of little algae organisms, we talked about the plankton, the algae out in the ocean, they secrete these little shells of calcite, the calcium carbonate. That is actually what is the chemical makeup of chalk. So as I'm writing on the board, I'm like spewing out all these little, long dead, but little algae organisms that left behind those little shells, microscopic shells. So calcite or calcium carbonate. That's also the ingredient in Tums. Remember how that neutralized the acid when I put the hydrochloric acid on it? And so that's what it does in your stomach. You have hydrochloric acid in your stomach and you eat the Tums or the calcite, calcium carbonate, and it will help neutralize the acid in your stomach and make you feel a lot better. Or maybe you could just eat some chalk if you didn't have the Tums around. Probably won't taste very good. But so some of the uses of our carbonate minerals. Okay. Last, I do want to show you, because that was the end of those, in Arkansas, a few things of our resources. You won't be able to probably see all the details of this, and that's okay. Just a general idea here is what I'm going for. But here's kind of the state of Arkansas map and some of our mineral kind of resources that we have. So across the northern part of the state, you see here, we've got dolomite, beds of dolomite, so we do have some of that there. Let's see. Right there's a, can't see it very well, but it's got a little diamond shape to it. So here in Arkansas, we actually do have a diamond volcanic, it's ancient volcanic neck or pipe, we call it. No longer active, no volcanoes in Arkansas, but ancient. In Arkansas's geologic past, there was volcanism, and so this has brought up the diamonds. And so there's a diamond mine there called Crater of Diamonds. It's a state park that we have here in Arkansas. So the Crater of Diamonds State Park, and you can actually pay a small fee. I think it's $10. And you can go out and try to dig for diamonds, and they are finding diamonds there. Those little diamonds that you saw there were from the Crater of Diamonds. I didn't find them. It seems like every time I go, a week or so later, someone's found a diamond. But it's just a lot of fun to go out there and dig for the diamonds. But we have that where it's open to the public to mine for diamonds, so you might try your luck on that. Yeah, so we do have some of this limestone, which is made up of calcite in there. The gypsum I referred to, we do have the gypsum resource as well. So, you know, clay, sands, and gravels are some of the resources that we have. So we have a little bit of mineralogy still here in Arkansas that is useful for us to be able to be productive in some of these minerals. Okay. So I believe that's going to conclude. Let's make sure there aren't any other PowerPoints that I might be forgetting. No, that is the end. That does conclude our Chapter 1, our mineral unit. And so this is going to get us ready, giving us our foundation to now in Chapter 2 start looking at the rocks and looking at the different rock types, the rock cycle. This is going to give us a better understanding of, well, how did the minerals form? Because the minerals are going to produce our rocks. Remember, rocks loosely are loose aggregates of minerals. So minerals are the building blocks of rocks. So this is a good place to stop. If you need to review anything, do that. I certainly enjoyed sharing our mineral collection with you today, and I hope you enjoyed that as well. So I will see you